Welcome to the lpc9351 and lpc9321 training overview module. The lpc9351 and the lpc9321 are single-chip microcontrollers designed for applications demanding high integration and low cost. The devices are based on a high-performance processor architecture that executes instructions in 2 to 4 clocks, which is 6 times the rate of a standard ADC 51. Many system-level functions have been incorporated into these devices in order to reduce component count, board space, and system cost. Agenda. We'll begin the presentation by introducing the NXP 8-bit microcontroller family. We will then focus on the LPC9351, starting with its clock system, analog features, and power management. Before we end the presentation, we will have a brief discussion on tools. NXP's 8-bit MCU value proposition. NXP's 8-bit MCU family is the industry leader for ADC 51 products with enhanced analog features. The family has a broad product portfolio, it is cost-effective and easy to use. The family concept with a scalable flash memory provides an easy migration path. The family offers a wide range of on-chip peripherals like 10-bit ADC, and serial interfaces like UART, SPI, and I2C. NXP gives a lot of importance to local application support. It gives the benefit of quick response time together with support in the local language. Let's look at the LPC900 family upgrades. Although the LPC9351 and the LPC9321 have the same memory support and pinning as the LPC935 and the lpc9321 respectively, many new features have been added. The new features include robust brownout detection, integrated ADC module with programmable gain amplifier and temperature sensor, readable RTC, clock switching on the fly, and enhanced watchdog reset. The performance of the new devices is also enhanced. The on-chip RC oscillator offers high noise rejection with a clock doubler at ±1% accuracy. The watchdog has a separate oscillator which has a frequency of 400 kHz calibrated to ±5% at room temperature. This oscillator can be used to save power when high clock frequency is not needed. The ADC 8-bit conversion time is now greater than or equal to 1.61 microseconds at an A to D clock of 8 MHz. AAC Q100 testability for automotive has been incorporated together with lower power consumption. LPC9351, 9321 derivatives. As shown, the devices offer the same level of support with regard to memory, timers, and serial interfaces. When it comes to analog features, these devices differ. The LPC9351 is a more featured device which includes 2 8-bit ADCs, 2 programmable gain amplifiers, temperature sensor, and analog comparators. The LPC9321 has 1 PGA, 2 analog comparators. These devices have the maximum operating speed of 18 MHz at 3.3 volts. LPC9351 is offered in the PLCC28 and TSSOP28 package. The LPC9321 has 3 package options: PLCC28, TSSOP28, and DIP28. Target application examples. The LPC9351 and the LPC9321 have a wide application base. This slide provides a list of applications under the different areas like industrial, consumer, medical, automotive, communications, and instrumentation where these devices would be an excellent fit. Now we'll specifically look at the LPC9351 starting with the block diagram. The entire LPC900 family is based on a 6 times accelerated ADC51 compatible core and has an operating range of 2.4 to 3.6 volts. The LPC9351 on-chip memories include 8 kilobytes of code flash, 512 bytes of dedicated on-chip data E-square, and 768 bytes of SRAM. There are two on-chip oscillators, 7.373 MHz on-chip RC oscillator with clock doubler and 400 kHz watchdog oscillator. There are two 16-bit general-purpose timers which can be used as counters or timers. The LPC9351 has a simple real-time clock or system timer that allows the user to continue running an accurate timer while the rest of the device is powered down. Capture Compare Unit or the CCU is a 16-bit timer with 16-bit reload on overflow capability. It offers 4 compare or PWM outputs with selectable polarity and 2 capture inputs with event counter and digital noise rejection filter. Analog features. As mentioned before, this device offers some strong analog features such as two 8-bit ADCs integrated with PGA and temperature sensor along with two analog comparators. Serial interfaces are provided in the form of SPI, UART and I2C. Let's look at the key features of the on-chip memories. As shown in the image, both the LPC9351 and the LPC9321 have the same configurations for memories. The 512 bytes data E-square can be used to save configuration parameters. The data E-square is SFR based and byte readable, writable and erasable. The users can read, write and fill the memory via 3 SFRs and 1 interrupt. The 8 kilobyte flash is divided into 8 sectors of 1 kilobyte. It supports in-application and in-system programming. The flash memory also provides fast page program and erase times of 2 milliseconds. The LPC9351 flash reliably stores memory contents even after 100K erase and program cycles. All devices support 768 bytes of data RAM. Clock structure. There are 4 different ways to clock the CPU. They are external crystal oscillator or resonator. The crystal oscillator can be optimized for low, medium or high frequency crystals covering a range from 20 kHz to 12 MHz. There are 3 options. The high speed oscillator option is a factory default setting and supports an external crystal or ceramic resonator in the range of 4 MHz to 12 MHz. The medium speed oscillator option supports an external crystal or ceramic resonator in the range of 100 kHz to 4 MHz. The low speed oscillator option supports an external crystal in the range of 20 kHz to 100 kHz. External clock source. In this configuration, the clock is derived from an external source driving the crystal 1 pin. The clock rate may be from 0 Hz up to 18 MHz. The crystal 2 pin may be used as a standard port configured as clock output. The frequency of this clock output is half that of the CPU clock. On-chip RC oscillator. The on-chip RC oscillator has a factory pre-programmed oscillator frequency of 7.373 MHz at an accuracy of ±1% at room temperature. With the clock doubler option, it can achieve 14.746 MHz. The high accuracy of the on-chip RC oscillator allows the use of the UART without the need for an external crystal or ceramic resonator. On-chip watchdog oscillator. The watchdog oscillator has a frequency of 400 kHz at an accuracy of ±5% at room temperature. This oscillator can be used to save power, when no high-speed, high-accuracy clock frequency is needed. The oscillator options like the clock doubler and the choice of clock source are configured in the user configuration byte 1 UCFG1 and user configuration byte 2 UCFG2. UCFG1 and UCFG2 are non-volatile bytes which are written when the flash memory is programmed. In this slide, the internals of the clocking structure is explained in more detail. Oscillator clock. Oscillator clock is a clock signal that has been selected from the available clock sources and is fed to the div-M register. The oscillator clock signal can be divided down to a slower frequency by the div-M register to save power when lower CPU performance is needed. CPU clock. The output clock from the div-M register is the CPU clock, also called as C clock. C clock is fed to the RTC, CPU, UART, and it also serves as the source for the peripheral clock. Peripheral clock. Peripheral clock or P clock is a clock signal feeding the peripherals. The peripherals run at half the CPU clock rate, therefore P clock is equal to C clock divided by 2. Compared with old LPC900 devices, external crystal can also clock the watchdog timer. Clock switching. Clock switching on the fly is possible between the four clock sources: the external crystal or resonator, external clock source, on-chip RC oscillator, and the on-chip watchdog oscillator. Clock switching can be achieved by configuring the clock control register. The clock OK bit is used as a flag. This bit gets set when the switching is completed. During reset, the clock control register values are derived from the non-volatile bytes UCFG1 and UCFG2. Finally, let's summarize the clock structure by highlighting its key improvements. On-chip oscillators. The on-chip RC oscillator is added with the clock doubler option to achieve the higher frequency of 14 MHz. The accuracy of the low-power 400 kHz watchdog oscillator is improved to ±5%. Watchdog timer clock source option. The watchdog timer now has three options to select its clock source: the watchdog oscillator, the external crystal, and P clock. Clock switching on the fly. The LPC9351 can implement clock switching on the fly between the different clock sources. The upcoming section is focused on the analog functionality. In this section, we will look at the ADC and DAC functions, programmable gain amplifier, temperature sensor, and analog comparators. Let's begin with the big picture and then we will individually look at all the functions. The LPC9351 has two 8-bit 4-channel multiplex successive approximation ADC converter modules sharing the same control logic. Two high-speed programmable gain amplifiers are integrated. The PGAs provide selectable gains of 2x, 4x, 8x, or 16x. An on-chip temperature sensor is integrated with one of the ADC modules and operates over a wide temperature range. Each A to D converter consists of a 4-input multiplexer which feeds a sample and hold circuit, providing an input signal to one of two comparator inputs. The control logic in combination with the SAR drives a DAC which provides the other input to the comparator. The output of the comparator is fed to the SAR. This slide brings out the key features of the ADC block. Two high-speed programmable gain amplifiers are integrated in each ADC module to improve the effective resolution of the ADC. An on-chip wide-range temperature sensor is integrated with the ADC0 module. It provides temperature sensing capability from -40°C to +85°C. The ADC now supports 8-bit conversion time of greater than or equal to 1.61 microseconds at an A to D clock of 8 MHz. Each A to D has 4 result registers. There are 6 operating modes and we will touch on this later. The A to D conversion can be started by using 4 start sources. Each A to D converter's DAC block can be output to a port pin. Finally, I have included the snapshot on the right to indicate that the lpc9351 has all the analog features and it is marked by the red box. Now that the overview is clear, let's look at PGA0 block diagram. 4 external analog input signals AD00 to AD03 can be selected to enter PGA0 by configuring the PGA input channel selection bits in the PGA0 control register. AD03 temperature sensor and the internal reference voltage multiplex to the same input channel of PGA0. The TSEL1 and TSEL0 bits help in selecting one of the 3 sources for PGA0. The gain of PGA can be programmed to 2, 4, 8 or 16 by configuring the shown bits. PGA0 is enabled by setting EN PGA0 bit. If the EN PGA0 bit is cleared, PGA0 is disabled and bypassed, which means the PGA gain value is 1. PGA calibration is needed to guarantee the linearity of PGA output when changing to a different gain level. PGA trim X bit is used as trim enable bit. If set, the PGA input is grounded for calibration mode. All the shown bits are part of the PGA0 control register. PGA outputs go into the 4-input multiplexer of A to D converter, allowing the amplified signal to be converted by the ADC. Let's look at the PGA1 block diagram. The structure of PGA1 is similar to PGA0. There are 4 external analog input pins AD10 to AD13. For PGA1, its outputs not only can be converted by the ADC but also pass to analog comparators for analog signal comparison. Let's move on to temperature sensor. The formulas for temperature sensing are listed on this slide. In the first formula, Vsen is computed from the A to D converted result of Vref and the A to D converted result of Vsen. The second formula shows the transfer function through which the temperature is computed. These are the key steps for computation. Select the internal reference voltage and then use the A to D to obtain a ref. Similarly, select the temperature sensor and obtain a sen. Calculate Vsen with formula 1. Calculate temperature using formula 2. The next slide highlights the hardware functions that enable the temperature computation. In this slide, we revisit PGA0. Although the temperature sensor signal is combined with PGA0, it can work without the PGA. Configure the PGA0 configuration register to the shown value to disable the PGA. As mentioned in the previous slide, we have to first compute a ref from Vref and then compute a sen from Vsen. The TSEL1 and TSEL0 bits are used to choose the internal reference voltage or temperature sensor, which then gets routed to the A to D. Configure A to D input select register by setting bit 3 to enable the 4th input for sampling and conversion. The A to D can now be used to compute a ref and a sen. Using these parameters, the temperature can be computed. Now let's look at the A to D or DAC block. The A to D conversion and DA conversions share the same conversion logic. So users need to choose either the A to D or the DAC function. The A to D can operate in 6 modes: single channel mode, single channel continuous mode, auto scan mode, auto scan continuous, dual channel mode, and single step mode. PGA Channel Selection. In some ADC operation modes, the PGA channel selection is dependent on the ADC channel selection, which means the PGA channel selection is tracking the ADC channel selection. In other modes, the PGA channel selection is independent and can be different from the ADC channel selection. If different, the gain of the selected ADC channel is 1. The table is giving the relationship of the PGA channel selection to the ADC operation mode. Let's try to illustrate this by an example. In this slide, we are showing the fixed channel single conversion operation mode of the ADC. In this mode, the PGA channel selection follows the ADC channel selection. Let's track the example step by step. In the PGA block, the second input of the ADC is selected. The gain of the PGA is set to 2x. Of course, PGA1 has to be enabled. Now, in the ADC side, the first input is selected for sampling and conversion. Also, the mode of operation is selected as fixed channel single conversion mode. In this mode, PGA channel selection is dependent on the ADC channel selection. It means PGA's own selection, which is AD11, is of no use because it will track the ADC channel selection, which is AD10. Hence, the first input of the ADC is selected by PGA1 and it is amplified by 2. The corresponding result register gets a conversion result of AD10, which is amplified by 2. Now let's look at the second example where the PGA channel selection is independent of the ADC channel selection. The PGA configuration is the same as before. A to D input selection is also the same. The mode selection is different. This time it is selected as fixed channel continuous conversion mode. In this mode, PGA channel selection is independent of the ADC channel selection. It means the PGA channel selection can be different from the ADC channel selection. If different, the gain of the selected A to D channel is 1. According to the PGA configuration, the second input of the ADC, AD11, is using the PGA, and AD10 will bypass the PGA. That means the gain is going to be 1. The result registers will get the conversion result of AD10, which is not amplified. Because of the continuous mode, the result of the conversions will be sequentially placed in the 4 result registers. AD1-0 will get the first conversion result of AD10, AD1-1 will get the second, and so on. Analog comparators. As mentioned before, the output of PGA1 goes to the ADC and to the analog comparators. 2 analog comparators are provided on the lpc9351 and the lpc9321. Input and output options allow the use of comparators in a number of different configurations. Comparator operation is such that the output is logic 1 when the positive input is greater than the negative input, otherwise the output is a 0. The positive inputs of the comparators can choose from external pins as shown. The negative inputs are selectable from a pin or an internal reference voltage. Each comparator may be configured to cause an interrupt when the output value changes. The comparator inputs can be amplified by using the PGA1 module. The PGA1 can supply gain factors of 2x, 4x, 8x or 16x, eliminating the need for external op-amps in the end application. Peripherals. Let's capture the remaining peripherals on the lpc9351. Serial interfaces will include SPI, UART and I2C. Timers will include general purpose timers, PWM, RTC, and watchdog. We'll end this section after reviewing interrupts. Serial interfaces. SPI is a full duplex, high-speed, synchronous communication bus with two operation modes, master mode and slave mode. Up to 3 megabits per second can be supported in either master or slave mode. The lpc9351 supports an enhanced UART that is compatible with the conventional ADC 51 UART, except that timer 2 overflow cannot be used as a baud rate source. It does include an independent baud rate generator. I2C bus uses two wires, serial clock and serial data, to transfer information between devices connected to the bus. It has the following features: bidirectional data transfer between master and slave. It can operate in a multi-master bus with no central master. Arbitration is possible between simultaneously transmitting masters without corruption of serial data on the bus. Timers. The lpc9351 has two general-purpose timers which are upward compatible with the ADC 51 timer 0 and timer 1. Both can be configured to operate either as timers or event counters. The lpc9351 has a simple real-time clock or system timer that allows a user to continue running an accurate timer while the rest of the device is powered down. The RTC can be used as an interrupt or a wake-up source. As shown in the image, the real-time clock is a 23-bit down counter which is comprised of a 7-bit prescaler and a 16-bit loadable down counter. There are 5 SFRs in this block. Users can now use two of the SFRs, RTC data high and RTC data low, to read the 16-bit counter portion of the RTC. The watchdog timer subsystem, as we know, protects the system from incorrect code execution. It has the following features. The watchdog timer can only be reset by a power on reset. It can be used in a special timer mode. The watchdog timer oscillator and the external crystal oscillator will continue to run in power down, consuming approximately 50 microamps as long as the watchdog oscillator is selected as a clock source for the watchdog. Capture Compare Unit or CCU. Let's highlight the key features of the CCU. The unit consists of a 16-bit timer with 16-bit reload on overflow register. There are 4 compare or PWM outputs with selectable polarity. The PWMs can be selected to be symmetrical or asymmetrical. 2 capture inputs are provided with event counter and digital noise rejection filter. I/O ports. The lpc9351 has 4 I/O ports: port 0, port 1, port 2 and port 3. Ports 0, 1 and 2 are 8-bit ports and port 3 is a 2-bit port. Up to 26 I/O pins are available. 8 of the I/O pins are capable of sourcing and sinking high currents, 20 milliamps. They are highlighted in the pinning diagram as P0.3 to P0.7, P1.4, P1.6 and P1.7. Interrupt handling. This table shows the 15 interrupt sources of the lpc9351. lpc9351 uses a 4 priority level interrupt structure, with level 0 being the lowest priority. This allows greater flexibility in controlling the handling of the device's 15 interrupt sources. If requests of the same priority level are pending at the start of an instruction cycle, an internal polling sequence determines which request is serviced. This is called arbitration ranking. The user manual explains priority and arbitration ranking in quite some detail. Let's look at some of the special interrupt sources. The keypad interrupt function is intended primarily to allow a single interrupt to be generated when port 0 is equal to or not equal to a certain pattern. This function can be used for bus address recognition or keypad recognition. The device also has two external interrupt inputs in addition to the keypad interrupt function. Let's move on to the power monitoring functions. In this section we will cover BOD, power on detect, and power reduction modes. Robust brownout detection. The BOD block has three independent functions: BOD reset, BOD interrupt, and BOD E2 flash. BOD reset will cause a processor reset and it is always on, except in total power down mode. It cannot be disabled in software. The selectable voltage levels include 2.2, 2.4, and 3 volts. BOD interrupt will generate an interrupt and could be enabled or disabled in software. The selectable voltage levels include 2.4, 2.6, and 3.2 volts. Please note that the trip point of the BOD reset should be lower than the BOD interrupt. BOD E2 flash is used for program erase protection. The trip voltage level is 2.4 volts. It is always active except in power down modes. The power on detect has a function similar to the brownout detect, but is designed to work as power initially comes up before the power supply voltage reaches a level where the BOD can function. The POF flag is set to indicate an initial power on condition, and it will remain set until cleared by software. Power reduction modes. The lpc9351 can operate in 4 modes: normal, idle, power down, and total power down. In normal mode there is no power reduction. In idle mode the peripherals are running and they can activate the processor when an interrupt is generated. In the next two slides we'll focus more on power down and total power down. Power down and total power down. In power down mode, the oscillator is stopped and the power supply can be dropped to the RAM keep alive voltage. Total power down is the same as power down, with addition of BOD and the voltage regulators also being shut down. The table gives the supply currents in different test conditions for power down and total power down modes. As also shown in the table, users can enable or disable the watchdog timer or RTC flexibly according to the specific needs of the application. Enabling these peripherals in low power down mode can increase current consumption. The graph shows the supply current in power down mode and total power down mode at different temperatures. The data in power down mode are measured using an external clock with the following functions disabled: comparators, real-time clock, and watchdog timer. From the graph we can see that the typical supply current in power down mode is less than 20 microamps. In total power down mode, brownout detect is also disabled. From the graph we can see that the typical supply current in total power down mode is less than 1 microamp. The NXP 8-bit family has got full development tool support from leading 8-bit tool vendors. Let's look at programmers, emulators, evaluation boards, and software support for the lpc9351. Programmers. On the right hand side you will see programmer models from Zeltec and Systems General. The Zeltec programmers have a USB interface and support up to 430 socket adapters. The 3000U and 9000U models also support standalone mode. Systems General also has similar offerings. This slide provides information on programmers from two other vendors. Emulator. The Keil EPM900 LPC emulator can support lpc9351 with the lpc9351 bond-out chip. It supports in-circuit debugging in target hardware via a 28-pin socket interface. The Wave V8 series is a general emulator. It can support the Keil software platform and provides signal trace and analysis. Wave 93X is an emulator built specially for the LPC900 family. The TK Scope series supports Keil and IAR software. It has a high-speed USB interface and it can support signal trace and analysis. It will be available in Q209. The web links will provide detailed information on the respective emulators. MCB900, Kickstart Kit, and DP93X can be used as evaluation boards for the LPC9351. Please visit the shown web links for detailed information. Software: Keil Microvision 3 for C51, IAR Embedded Workbench for 8051, and Resonance Write are complete development environments with compiler, assembler, linker, locator, simulator, and editor. Embedded Systems Academy also provides a FlashMagic software which can be used for ISP programming. This slide provides a snapshot of the application note support that will be offered with the LPC9351 devices. In this final slide, a table is provided that shows the comparison between LPC935 and LPC9351. Customers who would like to migrate to the LPC9351 will find this information useful. Of course, the datasheet and the user's manual would provide the most detailed information in this regard. Pinning, memory support, and flash programming options will remain the same, so when migrating to the LPC9351, hardware modifications are not needed. The improvement and new features are in the form of the clock structure, BOD, ADC, and power management. This brings us to an end of the LPC9351 and LPC9321 overview presentation. Please leave your feedback and any suggestions that you might have in the comment box. Your inputs will help us improve the training experience in the LPC zone. We are adding new training modules all the time at nxp.com/lpczone. So we encourage you to register and we will send you email updates when new videos get uploaded. Thanks for watching this video and we look forward to seeing you again.